usually opens okay?
I generally get
So let me ask before we get going. By the way, I'm Carl Salvaggio for those of you who don't know. Part of the digital image remote sensing lab. Hence my teaching remote sensing class. What we're going to do this quarter builds a lot off of radiometry. So does everybody have radiometry? All right, cool. All right, so this is first of a 2-quarter sequence in remote sensing as a baseline. There's a lot of electives that come after this. What we hope to do is get you used to the kind of remote sensing that we do here at RET, which is different than remote sensing you'll see in a lot of other places in some ways, and it's similar in many others. The textbook that we're going to be using is Remote Sensing in a Chain Approach. It's that one right there. And it's that's in the 2nd edition, and I think I got all the chapters and stuff matched up because I had the 1st edition. I realized that I think everything's fixed. So if anything seems not to line up, I'll make sure I correct that. All right. Just a little logistics. I very much dislike my courses. All right, so I don't use it because every time I use it, I lose something. I don't know why. So I just have everything out on my own site. So if you want to get here, you could write down that URL and never have to worry about it. You can go right there. Or you can go off the main CIS webpage. Let me just go there real quick. You go to the most horrible webpage in the world. And then you try to find somebody, go to people. Go to faculty. Before I do that, hold on 1 second. Record.
Are there any distance learning students?
There are 2.
I'm actually one of them.
You're not very distant.
Yes.
Okay.
I'm actually from Phoenix. I'm here talking.
You mean with Mike today? Or?
Yes.
Okay. Awesome.
So I actually get to sit in on the real time.
Cool. All right, so that's all right.
Do you have a 31st one? Or the 29th? Sorry.
I'll fix that later. All right, so you get to look at all the wonderful faces. And there. All right, so if you click on that, you go to these little pages. If you go down a little bit, you go to a personal web page. Right? I would just recommend bookmarking this after you do it. You get there, then I got all my courses right here. So this is 762. And that should take you in. It'll ask you for your username and password. That's your RAT username and password, not your CIS one. And once you put that in, you'll be in. And everything will be right here. The outline for the course is right here at the end of the course description. Very few words in there, but the topics are all there, all set to go. The reading materials that we're going to use throughout the quarter, PDFs around here for some articles and stuff that we have. The textbook's going to be the main source that we use throughout the quarter. And I would just recommend keeping up with the reading in the textbook, and everything should be really clear. All the course notes are out here by chapter in the textbook. These are John Schott's course notes. So if I go into one of these, you're going to see John Schott. That's not me. But it turns out that the materials in here are not very, let me say, innovative by any means. They're pictures out of the book. All right, they're just kind of talking points. So I wouldn't even recommend downloading these because everything's right in the book. If there's some stuff that's interesting, go ahead and download it. But he did put this little copyright thing on it. So that's why I'm not stealing the stuff. I'm just going to use this notes directly. All right, so they're there for all the rest. There's a couple ancillary ones down here, and I'll probably put more there as the quarter goes on, as I'm not happy with the other notes. What we're going to do this quarter, we're going to have 3 laboratories. right? They're not laboratories in the sense that you're going to go into a lab and work, but they're projects to work on. They'll be spread out over the quarter. We'll probably assign the first one next class on Thursday. And those 3 are going to be 5% apiece. They'll make up 15% of the grade, and then there's going to be 3 exams, and that'll make up the other 85. And I think the first one will be 25, and then 35. Yeah, 25, 35, and 35 will make up the 3 exams. I'll have the first one right before the break, so you don't have to take 3 weeks off and come back and take an exam on stuff that you learned right before the break. Right, so you don't have to worry about this too much. All right, there's going to be a couple files and that kind of stuff that you need, images and that sort of thing that'll be out here in laboratory materials eventually, once we get all that organized. And when you want to go ahead and submit something, I just use my own submit system here. So here's your 3 projects. You go ahead, you click on one of those, upload your files, however many you want. If there's more than 6, you did too much work. You just do another page. Just put your username in there, RT username, hit submit. You'll get an email back telling you everything is successful. And if you miss a lecture, or you want to, if you're sick, stay home. You can watch live right here, right? Just click on here, and you can watch it live anytime. I'm just going to do everything with Connect. And if you want to be missing something for one reason or another, they'll all be posted out here by date. Then you can watch after the fact. So the 3 exams, like I said, Thursday right before break, end of January, and then last day of class. I have to travel. I know I have to travel 3 days this quarter, so that's strategically placed 2 of the exams. And this day right here, we'll see how we're doing. If we're not caught up, or if we're not a little bit ahead, I might have somebody come in and do that one particular lecture. You don't like to have somebody, okay, everybody say, no, we don't like this, okay. If I'm, where am I going to be? I'm going to be in San Francisco. You don't want me to sit in my hotel room and give a lecture, you come here and watch it, right? All right, so I'll try and get somebody live and in the flesh here, because I hate doing that. There's nothing, I mean, it's really, have you ever done that? You ever tried to deliver something remotely? You sit there and you're talking to your computer and you're like, wow, this is very, very strange. And there's about a 5-second delay. So if I'm trying to listen to you guys too so you can ask questions, I hear myself 5 seconds after I spoke. And it's very hard to talk that way. All right. So that's the logistics. Any questions on that? As far as DL goes, have you taken a DL class?
Yeah.
Before? Okay, Cindy, you worked with Cindy Schultz? She's going to work with you again to do all the exams and that sort of thing. All right. What is that other camera? What's going on there?
There's a camera recording the...
Oh, it's just recording outside?
Yeah.
Is it saying in the corner about someone wanting to enter the room? I don't know if you have to allow people to watch the lecture.
Thank you. Just make sure. Greg, can you hear? Sweet. All right. All right, so like I said, we want to talk about what remote sensing is like here at RT. You know, so as far as we're concerned, what is remote sensing? All right. If you want to, look at the formal definition of what remote sensing is, it's really trying to learn something about something in the world, an object, target, phenomenon, something that you can observe when you don't physically interact with that particular phenomenon. All right. So for instance, if I wanted to determine what color that wall was sitting over there, well, with my human visual system, I can look at it with memory and things I've been taught. I would say that is off-white, all right? And that's a sort of remote sensing system. I have a physical phenomenon going on over there. It's a material. That material is painted. Right? That paint has reflective properties due to the chemical composition of it. It scatters in a particular way. There's sources in the room that reflect off of there. The sources go off the wall, reflect towards me. I see it. Right? It travels through this media in the room. It's pretty clear. There's not a lot of scattering that goes on between me and there, at least in the wavelength regions that I can see. Then it goes through my lens of my eye, gets focused on my retina. Oh, yeah, okay. I'm not a vision guy. All right, and then somehow that gets converted into electrical signals, and my brain interprets it. All right, so that's a complete imaging system that I'm using. And in the end, where's the processing getting done? Well, the processing is from my experience. It's because I've seen this before. Well, I could take a camera, like the camera in the back of the room, and I can point it at the wall. And then I can look at the digital counts that get recorded on the camera, and I could maybe take the RGB digital counts. There's only 3 bands in there, but I could look at 3 bands. And from those 3 bands, perhaps I could quantitatively figure out what the color of that wall is. So that's one sort of remote sensing. If I put someone in an MRI machine and image them, that's a sort of remote sensing. We're learning something about a material or an object or a subject without touching it. Right? All that's remote sensing. That's not what we do in the remote sensing lab. A lot of people do that from the center. We kind of look at it, this is a center for remote sensing, not really a center for imaging science. And everybody does some sort of remote sensing. I'm recording, but that's okay. I really do that. But what we do is we try to do Earth observation. All right, so we look at remote sensing as an Earth observation sort of discipline. Pretty much everybody in our lab looks that way. But that being said, I work on a lot of other projects that I consider remote sensing. I do them with people in a remote sensing laboratory. For instance, I'm currently looking at psoriasis patients and trying to figure out how we can score severity of psoriasis on folks and be able to automatically prescribe to them the pharmaceutical that's helped them. Well, what am I doing? I'm using thermal infrared imaging, I'm using UV illumination, I'm using all sorts of things that we use in remote sensing when we look at the Earth, but I'm looking at another phenomenon. Right? So it's still considered that remote sensing. So it's a very broad definition, but the things that we'll do in here primarily will be Earth observation. Either from a platform, like a rooftop or a tower, from an aircraft that we're flying, or from a satellite sort of system that we're looking at here from space. All right, so why is remote sensing growing as fast as it is? And it's still a very quickly growing field. Well, not too long ago, probably late 1950s, beginning of the 1960s. So this field's only about, in the form that it is now, about 50 years old. We were able to get the first images from space when the first unmanned rockets went up. Well, this one was from Skylab, so that was in the 1970s. But if you can look at an image like this and all of a sudden see the entire world, I mean, it was the first time that we saw the Earth. Right? Once we put a camera into space and looked down, it was the first time we saw the Earth. It was the first time we were really sure it was round, right? And when you see all of that going on at one time, you see the clouds, you see the continental masses, you see the oceans. All that information is all of a sudden presented to you for the first time in one view. Right? So this is what John refers to in his book as a synoptic view of the world, where you can see all the systems that are interacting together at one time. And from that, you get a little bit more information, right? So I'm the worst geographer in the world. Anybody have any idea where that is?
Northern Africa and Europe.
Northern
Yeah.
Africa and Europe?
I'd agree with that.
We're going to go with Northern Africa and Europe because I have nothing better. You know, but if you work down on Northern Africa, all right. So let's say we're in Northern Africa and we're standing on the ground right at that location. You look around you, and most likely, from what I'm seeing right here, you might be in the middle of a deserted area, right? So you see sand around you. You look out the ground, you see sand. Well, now you have a little bit of information, right? Your remote sensing system, you look at the ground, you know you're in sand, and you have no water, and you know you're in trouble, right? So you think about that, and that's all the information you have. Right, now, if you back out a little bit, you zoom, you know, fly up a little bit, now you might see, you know, that over the mountain, there's a city that you can get to. You might know a little bit more about that. Go a little bit higher, you might see the continent that you're on. Now you might have a good idea of where you're located. Well, you move up a little bit more, now you might see the clouds that are there, and you might get some inference about the weather patterns that might be coming along, right? So you just get more and more information as you move further and further out. Okay? So that's why remote sensing all of a sudden became very exciting to a lot of folks. And you know, this was just a photograph with color film, and that carried us for a very, very long time. You know, using just conventional film systems in cameras from airplanes or from satellites or from manned spacecraft, that carried us for a very, very long time. I would say up through the early 1970s, right? By the time we finally went to some electro-optical sorts of systems that were out there. All right, so this is what, you know, kind of spurred everything to move on. Now, it's not just the images that are fun, right? But we can make products from these images. For instance, this is a map of the what's called the normalized difference vegetative index. All right, colors in this particular image indicate the vigor or the health of vegetation, or really the biomass that's located in a particular area. So these dark green areas that you see over here are highly forested areas, very dense sorts of forests. The browns that you see out here in the western part of the U.S. and down through Mexico, these are the areas where there's not a lot of vegetation on the ground. It's mostly, you know, bare exposed soil and rocks and things like that. All right, so the scale that goes from totally unvegetated, which is the ocean, to brown, which is the deserted area, out to these very lush greens, which are the very dense biomass areas. Now all of a sudden, this is a product that you can produce from remote sensing imagery, from the imagery that you actually collect, and make a product that you give to somebody to give them information, right? And that's our whole purpose here, is to take imagery and somehow get information out to a user, an analyst, you know, you name the kind of person who's going to use this, but the idea is to try to get that information to them. All right, so, and it was produced by Canadians. You see that? These guys are smart. All right. So that's what you could do with that particular image, was made with what's called color infrared imagery. I'll show you a little bit more color infrared stuff as we go along here. This example image is from the heat capacity mapping mission, and this is thermal imagery. All right. The only reason I'm not geographically challenged here is I used to live right here. This is the Washington D.C. area. And this is the Delmarva Peninsula and the Atlantic Ocean. And the way this image is coded is it's coded according to temperature. Right? So the redder colors here are the warmer areas, and in this particular case, this is coded a little weird. The green area right here is cool, and I don't know why this was coded the particular way it was. But you, oh, I'm sorry, no, I'm sorry, the green is warm water. So the red's the hottest, the blue's the coldest, the green's somewhere in the middle. And you can see that, where is it warmest? Well, it's around those areas that you have a high density of urban sorts of populations. Right? So around the Washington, D.C. area, for instance, right here. The southern tip of New Jersey, so the Atlantic City sort of area over here. The area that comes true right here is actually part of the Gulf Stream, right? So this is a current that's coming up, and it's actually a very small, not small, but a fairly small, by global scale area of concentrated water of different densities traveling at a different temperature. So with this kind of a system, we can see, those sort of phenomena that go on. You always heard about the Gulf Stream. Well, it's kind of cool to be able to see it mapped out. All right, this is a color infrared image. I just mentioned color infrared a second ago. What color infrared imagery is, it was developed between World War I and World War II, and it was primarily developed to assist the military in detecting camouflage. Right? And we'll take a look at some camouflage detection stuff in a second here. But what are its characteristics? Well, when you think about color film, you think about red, green, and blue. Right? You record red, green, and blue information, you produce a true color image, very similar to what you see with the human eye. Color infrared film, what it does is kind of shifts a little bit, and the blue channel in color infrared film is actually green information. The green channel is actually red information, and the red channel is actually infrared information. Right? So the spectrum is sort of shifted a little bit, and it's not shifted in a physical sense, it's just shifted in the way that we represent it. So things that are bright red here have a very high infrared reflectance. It's not because they're red on the ground, it's because it has a very high infrared reflectance. So this is actually a very lush green forest that we're looking at right here. And these are roadways that are running through that forest. And these trees are very green if you were to look at them, but they appear red here because the spectral reflectance of chlorophyll is actually very high in the infrared portion of the spectrum. We're talking around 0.9 to 1 micron. Okay, so sort of those areas. All right, now this is sort of a neat image to look at in a couple different ways. So I wish those words weren't on this. Don't read the words. Don't read the words. Right? All right, don't just look at the images. All right, so look at that image, and what do you notice as you go from the bottom of this image up to the top? What do you see that appears a little different?
Lighter.
It seems brighter, right? So you sort of have this bright spot up in the upper left-hand corner.
Contrast is different.
Contrast is different, all right? What's making the contrast different? What do you think? Where are these dark areas down here? Shadows. Where do shadows go?
There are sensors overhead in that areas up top. So you're not the shadow. There is no shadow if you're right overhead. It's below.
The objects.
Close to that. So in this particular scene, what we're seeing is this area up here. If we look at this area, our aircraft is actually right overhead. Right? So we're looking straight down, but we're actually looking straight down at this point where my cursor is right now. Right? Where's the sun? Where do you think the sun is? Everybody's going like this. I have no idea where it is.
Top left.
Here? Up in the top left?
Bottom right.
Bottom right?
Doesn't it cast shadows the other way? The shadows are going down, and then the sun would have to be up.
There.
Well, the shadows are going to the upper left.
They are?
Yes, because the sun, you're absolutely right, is down lower right. And the reason you don't see the shadows is the tree is in front of the shadow.
Sound?
Right? So imagine, go outside if the sun, I don't know if the sun's shining today. If the sun's shining today, go outside and think about it. You have a shadow sitting in front of you. If the camera was behind you, looking at the back of your head and the shadow was in front of you, would you see the shadow? Your body would be totally blocking the shadow. Okay? So that's actually what's happening. And how can we prove this? Well, I don't know if this is proof, but it's pretty good. This is a blow up down here of that area right here. That's actually the shadow of the airplane. Right? So if the airplane was straight overhead at this location, then the sun has to be over here to cast a shadow of the plane over here. So you actually see the shadow of the airplane, so that kind of helps us out. All right. That's just a fun image to look at. But that's the kind of things you have to think about, right? When you're looking at this data, It looks like a picture, right? It's very easy to look at it and say, okay, it's a forest, these are roads. But when you start to look a little bit deeper and you try to understand all the phenomena that's going on, you got to wonder what's happening. You know, these things are brighter up here. Why are they brighter? Well, they're not brighter because they're different biomass concentrations or different chlorophyll concentrations. It's only brighter because you see less shadow. So if you're trying to do a quantitative analysis of this image and trying to make a map of biomass, you got to make sure that the algorithm or the technique that you use isn't going to get fooled by the lack of shadows that are there. Right? So when you're looking at this data, you got to look a little bit deeper, trying to understand all the phenomenology. I always tell all of my grad students who work with me, when they look at an image for the first time, it's easy just to see stuff, but to understand the phenomenology, that's what makes you a good remote sensor. To really think about what's going on in that image. What are all the physics? What are all the chemical processes? You name it. What's going on in that scene? Why does it look the way it does? Right? So that's what I want you to try and do throughout this course, and your next courses, and all your courses that you take in remote sensing, all your research. Always think about why you're seeing what you're seeing. Right? A lot of that comes with experience. You're going to make a lot of wrong decisions. I've made plenty of wrong decisions over the years. And you learn from each one of those, and you get smarter and smarter as you move along here. All right, so why do we make particular sensors, particular remote sensing systems to do Earth observation with? Well, we have this thing between the ground and our platform, whether that be in space or whether it be an aircraft or just on top of the tower. We have this media between the sensor and the target, which is the atmosphere. And the atmosphere is going to be a nemesis throughout your remote sensing careers and all your remote sensing studies, because it's always going to impart on your data information that really isn't what you care to look about. Unless you're an atmospheric person, then you care about the atmosphere. But if you want to know what's going on the ground, the first thing you want to do is try and get rid of this thing. Now, if you look at this, what we're looking at here is a transmission curve. And did you guys touch Modtran at all in radiometry? Okay, we're gonna do Modtran here. I just wanted to make sure you didn't do it already. And this is a plot that we generated using Modtran. Modtran is a model that predicts all the atmospheric characteristics very, very, very well. And this particular plot is just the atmospheric transmission as a function of wavelength out to 25 microns. So the visible portion of the spectrum is right down here. Here's about 1 micron, 800 microns is right here. So 700, 600, 500. So this is the area right here where we see every day. And if you look at that curve, well, it's really convenient that we have a very high 80%, 90% sort of transmission that we can see through this atmosphere. If we couldn't see through it, we wouldn't be able to have sensors that we're able to see in this wavelength region. Well, that's probably why we've adapted over millions of years, and our optical systems that we have adapted that way so we can see in these wavelength regions. Well, as you move further and further out, as you go out to 2 microns, 3 microns, further, you'll notice that all of a sudden there's these very deep lines that fall down to 0 in many places in the transmission curve. And these are atmospherically opaque windows. We cannot see through these. No matter what we do, there's no energy that gets from the Earth to a sensor over any nominal distance. Some of these, it only takes about 3 feet of atmosphere, and you have total opaqueness right here. I work a lot with thermal infrared, so this is my favorite window over here. But right here and right here on each side of the thermal infrared window, if I have 3 or 4 feet of atmosphere, and I have a sensor here and an object over here, and my sensor was sensitive at, let's say, 7.5 microns or so, something about right there, I won't see a thing. Everything is totally absorbed in that very short path. All right, so what causes these things? Well, it's gases in the atmosphere. On both sides of the long-wave infrared window, there's water absorption lines, and you just can't see them. There's carbon dioxide absorption lines right here in the 3 to 5 window, and right here in the 3 to 5 window, and you have these all throughout. So this really drives the sensors that we make. It only makes sense to design sensors that have spectral responses or filters on them that will allow us to see in the areas where we're actually going to get energy. So as we go through the course here, we'll look at a whole bunch of different imaging systems, and we'll refer to imaging systems that look in the UV, something that looks in the visible and the near infrared. Near infrared we usually find out to about 1.1 microns, and that's when we hit this first absorption. Well, it's really also very convenient that the semiconductor material silicon, which we make silicon detectors out of, is also sensitive in that same region. So that's kind of cool. So that's why we use silicon detectors. That helps us in our first window here. In the next two windows, which people usually refer to as the shortwave infrared, and they usually call this one SWIR 1, this one SWIR 2, you have this deep absorption line in the middle. Well, we have indium antimonide sensors or gallium arsenide sensors that can look in these particular wavelength regions. Another semiconductor material that's sensitive. Well, that's convenient. As you move out here to the 3 to 5 window, 3 microns is about right here, 5 microns is about right there. We got this deep absorption line in the middle. We usually don't break this one up, and usually use something like an indium antimonide or a platinum silicide sensor, which is sensitive in this region. Then out here in the long wave infrared, typical material might be a mercury cadmium telluride sensor. That's probably the most popular sensing material out in this particular wavelength region. So if we want to design a detector, we're limited by the atmosphere, so we've got to be very careful to make sure we pick the windows right. We need to pick optics appropriately so they transmit. Also, if I put a piece of glass out here in thermal infrared, nothing's getting through glass. Right? I don't know if anybody's ever played with our, we have a couple of thermal infrared sensors, and if you never played one, you should ask Joe Powell tomorrow. It'll be a lot of fun. But you can take a piece of sheet glass, right? You know, take a frame that you have, take the glass out for a second, take an image of your face, so the camera will put a piece of glass in front of your face, you won't see through the glass. You won't see through your glasses. Right? You have glasses on, you won't see your eyes. Right? You don't see through them at all. It's a lot of fun. And the other fun part, you know, these are things you have to do to keep yourself amused. Right? Take a thermal infrared camera, take a picture of yourself, and then take a garbage bag, a hefty garbage bag, and put it in front of you. Right? You see right through it. It transmits perfectly into long wave infrared. I do this to fourth graders, and it really amazes them. And then I do it to grad students, and it really amazes them. so it is, and I do it to myself because it still amazes me. It's a lot of fun to try and figure out the physics of why you're seeing the things that you can see. All right. Now I've noticed that there's no clock in this room, and when I'm in slide mode, I have no clock up here. Do you guys like to take a break in the middle of class, or do you like to go for the full time? Okay, so somebody tell me about halfway through that it's time for a break, okay? Because I'll never remember, and I don't have any watch or anything, so let me try. All right, now as far as spaceborne sensors, everything we saw there so far has been from aircraft. There's lots of satellites orbiting the Earth. I mean, there's literally thousands of satellites that are in orbit around Earth. A good number of them are imaging-based satellites. There's all kinds of communication satellites. There's all kinds of satellites out there, but a good number of them are imaging satellites. These are images from the GO satellite. All right, and this satellite, you know, sees the entire hemisphere. And in this particular image, you can see the time of day is moving on. Right, so you can see that the sun is rising. You have full sunlight a little later in the day, and then the sun starts setting. Right? So if you can put a satellite at a particular location, have it sit at that location all the time, well, now all of a sudden you can not only see what's on the ground at a particular point in time, you can watch how things change over time. You can see how the cloud patterns move. You can see how they migrate across the Earth. You can see the dynamics of the changing of light, you know, due to the rotation of the Earth. And you know, those sorts of things are hard to do from the ground. So if you move out and you take this synoptic view of the Earth, you can really begin to see some things that we only imagined before. Yeah, sort of imagined. All right, this is a set of images from Landsat 7 and Landsat 5 satellites. Landsat series of satellites are one of our favorites around here. We've been working with them for, well, right from the beginning when Landsat 4 went up in 1982. Yeah, 1782. I was actually a junior at that time here, so I got to work with that data when it started coming in, and we're still on the Landsat calibration team for the thermal infrared channels of that sensor today. So we've been, right from the beginning, we've been working with the satellite. This particular image is sort of neat. These are our wildfires that were burning out west in Arizona. And there's actually two fires that were going on simultaneously. So here's a pre-fire image, June 5th, 2002. A couple weeks later, the fires that started burning, you can see the smoke that's rising from the fires themselves, and you can see the change in the land cover, right? Where you actually have burn scars on the ground. You can see over time, over the course of 8 days, those two fires actually merged, right? They're still burning up here in the western part of the image. And then a couple days later, about a week later, the fire burned itself out finally, or probably didn't burn itself out, it was probably extinguished. And you could see what was left behind, right? And the change in the landscape over the course of a 1 month period due to that fire. Right? So these, again, are things that we can have people on the ground. We have folks in the lab who do fire research, and they're on the ground, they're measuring these sorts of things, they're measuring the amount of fuel, and how hot the fuel burns, and all kind of things, and you can really model the dynamics of the fire. But until you get up a little bit and take a look from overhead, it's a little bit hard to see what might have happened spatially because you're so close to it.
What's band 7? Is that thermal data?
Band 7 is not, no. All right, so Landsat's a little weirdly numbered. Bands 1, 2, 3, 4, 5, and 7 are blue, green, red, SWIR 1, SWIR 2. And near infrared. So blue, green, red, near infrared, SWIR 1, SWIR 2. And then band 6 is the thermal band.
Okay.
So this is the band 7 here, which is shown in red, is out around 2.2 microns. And what's shown here in green is band 4, which is near infrared. And then band 2 is green, which is shown in blue. Right? So we do this all the time, just because it's fun. But what you want to try and do is you only ever have 3 bands, right? Whether you have film, whether you have a computer display, you name it, all we can see is RGB, right? That's our only display devices. So we're always stuck. If we have 6 bands on a sensor, we have to pick which 3 we want to look at. And if you look at them in different combinations, you see very different things. It's not because the ground is red here, right? But the red is very bright because the reflectance in band 7, which is at 2.2 microns, is very high. Right? So the charred material has a very high reflectance at 2.2 microns, and that's why it appears so red.
So why is the smoke, like in real life, the smoke is green?
It,
Is that what it's saying?
well, let's see. It has a bluish red and kind of a purpley sort of tinge to it. These are technical terms, right? Right? So it's a blue and a red mixture. So it has a high reflectance in the 2.2 micron band, and it has a high reflectance in the green. Now, it also has a high reflectance in the blue and in the red, which would make it white. Right? But we're not showing blue and red. We're only showing green. So we're combining the bright part of the visible spectrum with the bright part that we're seeing at 2.2 microns. Actually, it turns out that out in band 7, there's a very high emission line due to potassium when things burn, when natural vegetation burns. That's why they burn so brightly. Well, I actually have another image of that in a little bit here. All right. This is a set of images taken over a couple days. This is one of my most embarrassing parts of my remote sensing career. Right. So I was a grad student, and I got up to give a presentation, and I had this image. And this is an image of the upstate New York area. Right. This is Lake Ontario. This is Lake Erie. Rochester's right there. Buffalo's around there. And I was giving the presentation. I named Lake Ontario, and I named Lake Erie. You notice I stopped at that point? because I don't remember what these lakes are. And so I'm sitting up there, and I'm doing, it's the first time I'm giving a presentation to John Schott. And he's like, hey kid, what are the other lakes? I'm like, Michigan? And I was totally wrong. So from that point on, he came in the next day, he got me a little kid's puzzle that had FNAF, it was all in it. It was very, very embarrassing. But it was fun. And I still don't know these little things. So here's the image, and you know, you've been here for a couple months now, some of you have been here longer than that. We don't get a lot of totally clear days. There's a lot of cloud cover that sits around. We're not totally socked in by clouds all the time, but there's times when we are. And if you look at the large area, you can see the white areas in these images over the course of several days are very cloud covered. But there are little peaks of hope that we can see through, right? We can see the ground in all of these images. So from these 5 images, we can actually take the cloud-free pixels and make a cloud-free composite of the area over a several-day period. You have to be careful when you do this sort of thing because the illumination might change, right? So you might be, you know, a late day image, an early morning image. With this particular sensor, the illumination was pretty constant, so that was okay because this passes over the same place on the ground at the same time every day. So we were okay with that, but you know, things can actually change on the ground, right? But this is a short period of time, so things probably didn't change all that much. But these sort of techniques are neat to make cloud-free composites, but when somebody presents one of these things to you, when was the last time you actually saw this condition in the Rochester area? Right? You gotta then take a step back and say, okay, how did you make that data set? Is that a composite? You know, because if you're going to use this to exploit some information about the ground here, then you got to be careful. You know, if this is a composite, adjacent pixels might be from a month apart, so you got to be careful about the kind of conclusions that you might draw. All right, this is the same sensor, the AVHR, the Advanced Very High Resolution Radiometer that's flown by NOAA. And this is the North American continent. It's actually kind of hard to see through there, but what I want to show in this particular set of images is that these were all taken simultaneously. All right? These 2 images down here are thermal infrared channels. Right? So brightness here is related to temperature, where these channels are red and near infrared, so these are more related to visible reflectance and to chlorophyll content. Right? So you can see that, you know, the clouds look the same in these 2 images because they scatter very similarly in those wavelength regions. But when you get down to the long wave infrared and the mid wave infrared part of the spectrum, the clouds actually appear a little bit different. Right? And it could be because of the thickness of them, composition of them, and temperature of them that we're actually seeing here. Because here, we're not seeing so much the scattering caused by the clouds or the reflectance of solar illumination. In fact, here we're seeing no solar illumination because it's very, very low in that wavelength region, the long wave infrared. But here in the mid wave infrared, we still do see some. But the major driver of the appearance of the clouds that we see here is their actual temperature themselves and the amount of ice crystals or water molecules that are present in that location. And so another way we can actually use these kinds of systems. All right, this is just a fun image. This was an image formed of the U.S. At nighttime, so there's no solar illumination at all. And this was from the DNSP program, Defense Meteorological Satellite Program. And these sensors were, you know, sort of dual use. During the day, they can be used for meteorological monitoring. At night, they can be used to see also because they're very, very high sensitivity. Right? So I don't want to say they're night vision, but they have a very, very high sensitivity detector. So just a few photons will actually excite the particular pixel. This system is also used to look for missile launches. Right? So if a missile gets launched at a location, you get a bright flash. These systems are sitting there staring, and they're waiting to look for a hot pixel to show up. But this particular image was just taken you know, during the evening, and what you can see is all the major metropolitan areas that are lit up at nighttime. Right? So you can see, you know, the New York City, New Jersey area over here, the San Francisco peninsula over here, Los Angeles, San Diego, search area, and then, you know, Disneyland over there, etc. Texas. So it's kind of neat to see this because you can almost use this as a population map. Because where there's heavy population, there's going to be more light, more urban areas. All right, here's these are a couple thermal infrared images. One from the HCMM that we just saw previously, and you can see some of the lakes and the watershed areas in central Pennsylvania. This one is one of my favorite. This is an image that we took with a sensor that we used to fly here in the Deers lab. This was kind of cool. It's called a Bendix line scanner. It was a set about this big, had a spinning mirror in there, and it had a single detector, just one detector, not an imaging array or anything like that. And the mirror spun, and it projected that one detector onto the ground, and it looked at the ground at one point at a time, and then as the mirror spun, it spun on the line. As the aircraft flew forward, you can spin it again and get another line, and you move it forward and get another line. So you just had the spinning detector going around. Well, the detector itself was actually a mercury cadmium telluride detector. It was a thermal infrared detector, so it was sensitive to temperature differences. Right. Well, this was back in probably 1982 or so. So that was sort of state of the art, a single thermal infrared detector. Well, that's great. How do you form an image out of that? Well, what it actually did was we would record the electronic signal on this detector that would drive a visible LED, right, which was sort of state of the art at that time. And the LED would glow brighter or darker depending on the amount of signal it got from the thermal infrared detector. Well, all right, great. What do we do with that? Well, we actually took a piece of 2 1/4 photographic film and moved it along and scanned that LED back and forth. So it got brighter and darker and exposed the film one line at a time as the film was going across and the aircraft was flying forward and its mirror was spinning. So it was actually taking a signal from an infrared detector, making the LED light up brighter or darker depending on how many thermal infrared photons it saw, and then it used that LED to expose film, and then the film was actually the image that we got to see afterwards. Right? It's a lot easier now. Right? For $5,000, I just bought a 640 by 480 pixel thermal infrared balometer. Right? And I took it out. It's a USB. I plugged it into my computer. Shoot, it's awesome. Right? This thing was a very deal, but it made really nice imagery. And this is I don't know if anybody's ever been to Albany, New York, but this is the Albany, New York area. And just some of the interesting things that you might see here. This building right here, I think it's about 20 stories tall. And what do you think these bright lines that are going across the building are?
They're lit.
What's that?
Are they lit or not lit?
They're not. They're hotter, but they're not because they're lit.
Is there people in them?
That could be the case, but not the case in this particular situation. This particular situation, those floors are where all the HVAC units are located inside the building. So these are the floors that the elevator doesn't stop at as you go up in the building. This is where all the heating and air conditioning equipment is actually located. And it's not very well insulated because you can see right through to the outer surface. And with thermal infrared, as we talk about it a little bit more, we'll see that you only can see the first couple molecules of most objects. So you're not seeing deep inside, you're seeing an effect on the very surface of that building. This auditorium here, if you ever drive by Albany, you'll see this big building, it kind of looks like an egg. It's actually a performing arts center. And this area right here is the stage, right here, and then this is the seating area. So there's actually a show going on while this was taken. So in this case, there are a lot of people in the building, and the auditorium was warm in the seating area because they wanted to keep the people comfortable, plus the heat from the people themselves. And you actually saw the roof of the building warmer because the heat rose. And again, this wasn't a very well insulated building itself. These areas on the sides are all the electrical transformers that were located behind the walls outside of the seating area, and the exhaust for the electrical transformers to keep the heat out of the building so it didn't get too hot to drive all the lighting and stuff on stage. So thermal infrared imagery is just a lot of fun to look at because it's hard to figure out exactly what's going on everywhere. Once you do, it's sort of neat to see these sorts of things. All right. So we talked about visible cameras. We talked about SWIR cameras, near infrared or color infrared film, thermal infrared. We also look at radar sorts of systems. We traditionally, the Deer's Lab hasn't been a big radar house, and I want to say, you know, we only have a couple of projects in the area of radar right now, but we're trying to do more and more in that area. John Karekis is probably our resident expert, and Mike Hartley, also our resident expert on radar, and we do these kind of things in our deer stick model, which we'll talk about later in the quarter. So we're starting to get into this area a little bit. But a radar is different than all the other systems that we've looked at so far because it's an active sort of system. It's a system that serves as its own illuminator, right? Everything we've looked at so far, either we were using sunlight to reflect off objects and look at it, or the objects themselves in the thermal infrared region emit energy, and then you can detect that energy. Well, here, we actually have to emit the energy from the detector itself down onto the target and then watch for the reflection that comes back towards that target. So the imagery takes a little bit more thinking on your part to understand what's actually happening, because when you think about a shadow in a visible scene, well, we did that earlier, right? We kind of said, okay, well, the sun was over here, and we even had trouble doing that, and that's what we see every day, right? So with a radar, your illumination source is coming from the same place that your detector is located. So your shadow is always, well, where would your shadows appear? In a radar system. If you're illuminating with a beam from your detector, and your target's over here, you shoot some energy down, it reflects off there and comes back and you detect it. Where does no energy get to? Where does no illumination get to? Behind it, right? So those are the areas that you're seeing that are dark. So it takes a little bit, you know, a little bit more thinking to think about what goes on there. All right. So what do we try to do? Well, we always love to come up with an equation for what we're trying to do in our remote sensing lab here. We want a functional relationship of some sort that lets us look at something in our imagery, something, some parameter, x1, x2, L, xn, you name it. You know, you name them anything you want. But we'd like to come back with a way to figure out what y is, right? Well, y could be anything. Y could be, let's go back to the example we looked at earlier with color infrared film. It could be the biomass. How much biomass is at a particular location on the ground, right? Well, what could that be a function of? Well, it could be a function of the infrared reflectance. It could be a function of the red reflectance. It could be a function of the time of the year. It could be a function of, you name it. You know, come up with all these parameters. What we would like to do is sort of form this, either a theoretical relationship between observables that we can see and measure with a remote sensing system and the actual observed phenomenon itself. Right? We can do that theoretically, we can do that through physics, or we can do it statistically. Right? We could say, hey, we have all this data that we collected, we have all these independent variables, right? Things that we measured, and we want to predict this dependent variable. Well, we can do that, like I said, with all the physics that make up that process, or through a statistical approach. And we do both, right? Because there's sometimes where the physics is either too hard to understand, right? And a lot of times we you know, admit that, admit defeat, and go back and drop on statistics, and that's all a problem for us. But we do that, you know, usually as last resort, because normally, you know, it's a lot easier to build your model when it's when it is physics-based, right? But pretty much in everything that we do, and the kind of remote sensing we do here, this is where we try to get to. We love it when this is a simple linear equation, y equals mx plus b, and we go through great pains to make it come out that way, even if it's a little bit wrong, right? But there's times, and as time has gone on in the lab here, we've actually done quadratic equations every so often. Or, you know, so we will take that next step. But a lot of the things that can be modeled in the world can actually be modeled very simply, right? And we'll see that as we go through here. And it's sort of interesting that these simple models do sometimes work. But in this case, you know, you can have a multivariate relationship on the right-hand side of the equation to predict any kind of variable. That's what we'd like to get to. All right, so when we look at stuff, look at materials on the ground, we need to understand something about it. And the biggest thing that we look at when we use remote sensing, when we use imaging sensors to do that, and we look at spectral sensors, so sensors that will image from many different wavelengths, is we rely on understanding the facts that different materials reflect or emit energy differently And these spectral signatures are, that we see here for all kinds of different things are really the bread and butter behind using remote sensing to identify an object on the ground or to tell the condition of an object on the ground in some way or form. So what do we see over here? These are reflectances. These are minerals, right? So we've got gypsum, kaolinite, and calcite over here. The wavelength region is similar to what we saw on the graphs that I showed earlier. I know you can't read that here, but it goes from about the low end of the visible out to about 2.5 microns, so out to that SWIR 2 area that we were looking at before. And if you look at these minerals, you can see that, what color are they? What color is that one? Yeah, it's pretty white, right? Gypsum, that's dry the stuff you put inside of drywall. Okay. Calcite down here. These again, you probably can't read the scales from where you're at. This goes 0 to 1, this goes 0 to 1, and then this goes 0 to 1, so they're sort of stacked the way they appear. But these are reflectances about 0.8, so calcite is also pretty white, right? Maybe it reflects a little bit less in the blue area, right? So maybe it appears a little reddish, a little greenish, so maybe a little yellowish, beige. It's on the wall. All right, and kaolinite over here has a lower reflectance in the blue and high reflectance in the red and green. So this one definitely has a yellowish tinge to it. All right, well, these aren't very interesting in this wavelength region because look as you go out a little bit further, all of a sudden you start getting all this structure in the materials themselves. And if I were to look at calcite and I were to look at gypsum in the visible wavelength region, do you think you'd be able to tell the difference from what you're seeing right here? They both appear pretty white, right? By the time you realize that tungsten sources, if you're looking inside, have very weak blue output, and silicon detectors, the spectral response function for them falls off into blue. All of a sudden, you might not have a lot of faith in the blue area, which is really the only area here that's sort of distinguishing between these two. So your sensor might be limiting what you can do, right? But if you go out a little bit further, and you were able to look and see these little dips in the spectra, well, they're not here in calcite, but they're there in gypsum. Now all of a sudden you have a very telltale signature of what these materials are, right? So that's why we'd like to expand our vision beyond, but beyond the visible spectrum, so we can see a little bit further out and see some of these distinguishing features that are out there. All right, so those are solid materials. Down here is water, all right? And, well, this is, wait, where's the water? Oh, no, there's the water, I'm sorry. There's natural materials. So we got a lawn, a nice green lawn, so this might be somebody's front yard. We got some leaves, got some blue spruce trees going through here. We got some dry grass going through there. So it's all kind of grasses and vegetations. And if you notice the shapes look very similar, right? Between black bush leaves and green grass, right? You have the same dips in the same areas. You got 3 dips right there. Then you go down, and the shapes, even as you go out through the SWIR, don't change all that much, but their magnitudes change, right? So not only is it important to understand the shape of these spectral curves, but it's also important to understand the magnitudes of them. And that's where we've got to start to be really critical. We've got to make sure we get all our radiometry right so we can tell the difference between a 50% reflector and a 70% reflector. That's a pretty big difference. But you got to make sure your sensor's designed to be able to pick that sort of a change in magnitude up. All right, now, as you go out into the gaseous sorts of materials, so here's 3 gases that you might look at, you notice the spectral signatures are much different. Right? They have these very sharp, in this case we're showing absorption rather than reflectance, but these very sharp lines that represent their spectral signatures. Well, why is that? Any chemists? All right. I'm not a chemist either. Right? But now I can lie because you're no chemist. All right, well what happens? What is a gas? Well, a gas is a mixture of pure molecules, right? They're not formed together. So each of these molecules or each have bonds in them, and those bonds vibrate, right? Or they twist, or they rotate, right? So bonds do all these things, and as these things are happening, as there's a change between two atoms that make up a molecule and their distance, energy gets absorbed and emitted, right? And it happens in very pure gases. It happens at very specific frequencies that those energies get absorbed and emitted. And those are related directly to the kind of molecules that are there and the bonds that exist at those locations. Well, each of those bonds, or each of those vibrations, or twists, or rotations, forms one of these absorption lines in the spectrum, right? So a chemist can come in and say, oh, well, it's sulfur hexafluoride. Well, that has an absorption line at 4 microns and 10 microns and 20 microns, and they would know that right away. I would have to look it up in a book. But if you can see that full spectrum, and with this case, a thermal infrared sensor, now all of a sudden you can start to ID those gases that might exist. Yeah?
But those curves are like not continuous, right? It's like sample, because we have digital numbers or infinite number of wavelengths that we can measure.
Absolutely.
So if you have these kind of things, you definitely can miss.
You could definitely miss them. All right. So the problem here is that if we're sampling from, let's say, 3 microns out to 20 microns, let's say we only have 100 bands, so we're discretely sampling. In this case, we usually use something called a hyperspectral sensor. Right. Now, by definition, a hyperspectral sensor has wavelength bands that are the same width and touching each other. So there's overlap between the bands. Right? So we may have a band that has, let me try and draw it here, just freehand. If I might have a spectral response function that comes up here in sort of Gaussian shape and then comes down over here. Right? So I'll be integrating a much larger wavelength band than that particular absorption line exists in, but I should still get a sort of elevated signal. But you're absolutely right. If I have 2 adjacent bands, then I might have some overlap. This might be the tail of one spectral response function for a band on the left-hand side, and then on the right-hand side, in the middle of it for the one in the center. So I could actually get a response that's spread out rather than this nice peak. And in that case, you can do some linear system sorts of things where you could perform a deconvolution perhaps to sharpen that spectra. But now you're getting into an area where you're modifying the data that you collected. We do it all the time to try and do detection, but you're absolutely right that you have a problem. But the saving fact here is that the sensors that we typically use here have many spectral bands and they're touching one another. If they were a multispectral system, which we'll talk about the difference of these later, spectral bands could actually be several different areas where we don't sample at all. Then we have a lot of problems here. Great. So one last thing before we wrap up this little section is the title of the book that you're using is Remote Sensing Game Exchange Approach. And this is a term that the folks at Eastman Kodak a long time ago and us here at RIT kind of coined collaboratively to describe the kind of remote sensing that we do. All right? If you talk to folks at Kodak, they'll claim that they, or ITT, they'll claim that they made it up. If you talk to us, we'll say that we made it up. So I'll say we collaboratively made it up. But it's just sort of an idea that we use to try and explain what's going on here. Well, there's a lot happening, right? There's a material that we're looking at that has some physics going on inside of it. There's the sources, there's the atmosphere, there's the detector, there's the optics, there's the visual viewing of the data after the fact. All these things are individual pieces that really make up imaging science, right? That's why you're here. You're studying all these individual pieces of imaging systems. Right? We look at remote sensing as being or using all of those individual pieces of imaging science to make up what we do. So we, in a very simple case, we acquire an image, we do some processing on that image, and we put it on a display somewhere. Well, we could represent that as this chain that has 3 links in it. That's the image chain. And each link is a piece of that chain. It's a process that goes on. We could make those links smaller, right? So the image, the input or the acquisition, well, now we can start to look at the scattering properties of the material, the reflectance properties of the material, the atmosphere between the material and the sensor, the optics, the detector material itself. We can break it down this way. Well, notice this one is kind of a dotted link. That's supposed to indicate that it's a little weak, right? If we don't have a really good understanding of the atmosphere that was between the object that I was looking at and the detector, well, now all of a sudden we question everything that we see because we're saying, is that an atmospheric effect or is that a property of the material that I'm looking at, right? And if that ever becomes a question, that is going to put some error on your final answer that you give to somebody, right? If I'm trying to tell that color. Well, if I'm looking at this whole thing as a system, and I know I have a really great detector, and I know I really understand the physical properties of the material, but it's the atmosphere that is a little weak, well, that's the place where I should probably concentrate and try to understand that better. And rather than spending a little bit more money on a better detector because a new detector came out and I always have to have the newest detector, that might not be the best place to spend your cash. It might be better to go out and hire a meteorologist and be able to enhance that link, to make that link a little stronger so that even with your not state-of-the-art detector, you're going to improve the capability of answering the question. Right? So that's how we kind of like to look at this. And we use this image training example to sort of tell the story. But we want to understand all those pieces. We want to understand every single link in that chain. And we want to put our effort into taking those weakest links, the areas we don't understand the best, and trying to improve those. Right? Each one of those becomes a dissertation. Right? So if you're looking for projects, you will look for the weak links. That's where you can help improve the entire process. All right, so I am sure I've run past 9 o'clock.
It's 11 on the
Oh, wow, yeah, definitely that's not. 11. You want to take a short break, or
Yes.
You want to? Okay, yeah, take a short break. The actual Montreal, which exists only in the Linux world, and yeah, you could, not here though, because we don't load it. Yeah, it does exist for PC, but it's very expensive. We just use the free version.
I thought there was a free version for PC.
There might be.
Sorry.
No, that would be great if we had it. But we don't. I don't think we have it here. But if we do, then you can definitely do that. The reason I asked about and as far as coding wise, do people use MATLAB or IDL or something, Python? As long, because for one of these projects, we're going to have to run Montran a whole bunch of times. And if you have a proficiency with Linux and you can write bash scripts and do things like that, it might make work a little bit easier. So if you don't have that sort of a proficiency, you may just want to find somebody sitting somewhere else in the room that might be able to help you out with those little parts of it. Just because I don't want you to have to do all this by hand. But if you do these sorts of things, with sort of bash scripts in that particular case, that would work out. Now, along those lines, if you're in the course website here, if you come over here, general information, for some reason it's going off the other side. I think that's a little bit bigger. There is a TA for the course. If you just click on teaching assistant, Monica Cook's the TA. I think you had her for radiometry last quarter. All right, Monica's going to TA this course. She's going to have office hours up in, everybody knows where she sits on the 3rd floor, from 12 to 2 on both Tuesday and Thursday. So right after class, there's a 2-hour period. Monica is she won't admit this, but she's a whiz at doing this kind of stuff. So if you need help with a little bit of bash scripting and that sort of stuff, Monica can definitely steer you right. She's doing a whole bunch of this stuff for her dissertation right now. The other thing that we're going to have you do also, which we've never tried in the past, but I'd like to try it with you guys, is I'm going to have you all get accounts on our research computing systems here at RIT, which are large clusters of computing nodes. And as part of the Montran lab, there's one part in it where you got to run Montran 72 times by changing just one parameter inside of it. And that won't take a very long time. It'll probably take you about 2 hours of sitting there and changing things. But what we'd like to teach you to do is to take that job and farm it out to a cluster of nodes and have them all come back at one time. So rather than taking 2 hours, it should probably take about 2 minutes. It'll probably take you about 3 hours to figure out how to do it in 2 minutes. But it's one of those things that as you go on in your research, being able to use the research computing cluster help out the kind of processing that you're going to be doing, because I guarantee 80% of you are probably going to need to do that, some sort of very heavy, repetitive processing on whatever you do. You already have accounts that you'll already be able to go familiar with it. So we're going to try that for the first time. I don't know how it's going to work, because there are large research projects that go on campus. It's called research computing because it supports research, not classes. So I'm going to have to go beg to have them get us on there, but I think they'll do that. And just for the likelihood of having 10 new customers using their systems over there. So they're pretty nice systems to be able to use in the long run. So hopefully that'll work out. All right. So let's take a look at a bit more about remote sensing, getting into some of the things we're going to do here. All right. A lot of what I've mentioned so far, as far as remote sensing is concerned, is that we're going to make some algorithm, we're going to take some data, we're going to make some inputs to that algorithm, we're going to produce something. That equation that I put out there, y equals some function of some observed parameters, sort of implies that we're going to try and do this in a very algorithmic sort of fashion. But that's not how remote sensing started by any means. Remote sensing started in the field of photo interpretation, where people would sit down and look at a photograph and try to understand what's going on, right? Well, I mean, this started, back in, the eras of, the 1940s, and so we didn't have computing systems. We couldn't do complex algorithms. All we could do is collect the imagery and look at it. And so photo interpretation was the thing to do. I actually, after I left, I actually got my degree here many years ago, and then I left and I moved out to DC and I worked in the intelligence community for a long time. And I worked at the National Photographic Interpretation Center. So I was surrounded by analysts or photo interpreters every single day, and there seemed like thousands of them sitting everywhere. And a lot of the way the world still works is people look at images, right? Because it's very hard to teach an algorithm or a machine processing system of some sort, a computer vision system, you name it. You pick your favorite thing, genetic algorithm, you name your favorite sort of technology. It's very hard to make it emulate what a human can still do very easily. Right? So there was a guy named Estes who came out with a series of 7 cues to photo interpretation. Now, let me just walk through those real quick so you can sort of get an idea and an appreciation for what you can do, and then think about how you would have a machine do that, right? Some sort of computer vision system be able to do the same sort of thing. Right? So the first cue is shape. All right? So if we look at these images, right? These here, and we look at these particular features, A, B, and C. Right? Let me ask you one thing. Is A a natural object or a man-made object? Natural. Why? It's not linear.
It's not repetitive.
It's not repetitive. Right? And these are things you just know. Right? Because you've seen things before. You've learned over the course of your life that you're pretty sure that's a natural object. You're not 100% sure. Somebody could have made an object that looks like this, but most likely that's going to be a natural object. In fact, it's a flowing river. Right? How about this area right here? Well, it's a roadway, right? And that's a cloverleaf intersection, and you've seen that. How about this area right here? What is that? Yeah, it's a reservoir. Man-made or natural? You're guessing man-made. Why?
It looks like it's in an urban area.
Yeah.
If there's a lot of concrete and stuff, they need reservoirs for all the rain runoff, and there's lots of road stuff.
Yeah. So you're not only looking at the object itself, you're looking at the things around it when you try to make that interpretation. And there's 2 straight sides to it. Probably not going to happen in nature. And then a very regularly curved area on the upper side. So the shape of those things really implies to you something very clearly about what those objects are and whether they're man-made or natural, or even in fact what they are. You knew that one was a roadway. You knew that one was a reservoir. Right? You made those observations very clearly from the shape. How do you teach a machine vision system to do that same sort of a thing? Well, it's possible, right? But it's not trivial by any means. All right, now over here, we're going to look at the second cue, which is size. All right, and there's two blow-ups here. All right, so here's well, what are you seeing first of all? Just from size, all right? You're seeing, what are these? Those are houses, right? And what's over here?
Cemetery.
The cemetery, all right? And this blown up over here, a car, and this is a tombstone. All right, now look at the shape of that tombstone and the shape of that car. They're very similar to one another from shape, but the way these are blown up is a little bit misleading. But look at the size difference between the two, right? If you see a roof of a house, if you see a car next to that, you sort of get a scale of the roof. And then you see this, it's much smaller. It can't be a car, even though its shape is sort of similar to this, right? But it was very easy. What was the other thing that tipped you off this was a graveyard and these were tombstones? The arrangement of them,
Yeah.
right? The layout. Okay. Down here, water and ice. Okay. This is really, if you see this area, and you knew, and maybe if you zoomed out a little bit more, you'd see that this was a lake of some sort. But the fact that this goes from a dark area to a bright area, you know, if you knew that was a body of water, what would the assumption that you would immediately make is, oh, well, it's frozen and that's ice. And now all of a sudden, you would also know that it was probably in the cold season, right? And it was a cold day. And so you can make some further inferences about that. I just finished a project for the Department of Energy where I had to map water and ice differences automatically. And it wasn't as easy as it sounded, right? But by looking at the imagery, I was always able to tell. But to come up with algorithms to pick out the ice from the snow from the water was a pretty difficult task to do automatically and teach a machine to accomplish. Now, over here, this one's a little bit tougher, especially on this projector. But this area over here is forest. And this area over here is a lake, so it's water. But if you just look at their gray levels, they're the same in this particular wavelength band. And this is the red, it's a red channel, the color image. But if you could look closely, I don't know if you could see it, but there's definitely a texture that appears. And if you think about trees, what sort of a texture do you think about? Think about looking at the trees overhead.
Yeah, forest is going to be really variable, right?
It's going to be very variable. You won't see regular shapes. I mean, a lot of times, if you think of a model train set, you might think of these little round trees everywhere, but that's not the way it appears. But you definitely have a structure to each of those. And how about water? What's the structure of water?
It's not variable, right? Pretty constant.
Yeah, it's very constant typically. All right. So even though the gray levels are the same, the texture can kind of tip you off. So between shape and size and tone and texture, those are 4 cues that we use every day. And they're actually tough to get a machine to look at those. Now, what's that? Ooh, that's pretty close. This is a generational thing. Who's ever been to a drive-in theater? You know, that's a drive-in theater. And I immediately knew what that was, but it's kind of fun to ask you guys to see. That's the screen. That's the projection house. And this is the little hills that the cars park on when you pull in. If you've never been to a drive-in theater, about 30 miles south of here, in the summer, they have a drive-in theater that opens up. It's a blast. It's like $10 for a car full of people. You get to see 2 feature films. And you play the audio on your radio in your car. It's a lot of fun. All right, how about this one? Baseball field, right? And what immediately tips you off here? Well, it's the patterns, right? I mean, these little round hills, if you knew what a drive-in theater was, well, you'd immediately know that's where the cars park and that's a drive-in theater. And then all of a sudden you see, oh, there's the screen. Here, you have a very distinctive infield inside of, you know, the grassy area, so immediately you know it's a baseball field. Right? So patterns, or the changes in brightness within an area immediately tip you off to what something is. But if I looked at this big area here, how do I teach an algorithm, a computer vision algorithm, to say, oh, that's a drive-in theater? I mean, there's a lot that went into that, including the cognizance of what's driving the theater was, right? So you have to make sure your algorithms change. All right, so if you look over here, this is an indication of using a shadow to help you with the photo interpretation. So a cue from a shadow. What am I looking at there?
Fountain inside a building.
What was that?
A fountain.
A fountain? No, it's not a fountain. It's a flagpole. Right? How do you tell it's a flagpole when there's a big long shadow right here? Right? Without that, maybe you can guess a fountain's a very good guess. Right? Maybe it was a statue or something like that. But because it's so linear and thin, all of a sudden you know it's a flagpole. Right? So again, that's a very difficult thing to teach an algorithm to look at and understand. Sight's sort of a strange term, but it's the context in which you see something. Right? So let's look at this image in little pieces. If I looked at this area over here, what would you say that was? Maybe a parking lot. And what are these things? Maybe a football field.
That's a long one.
If it was a football field, what would these be?
Bleachers.
Those would be bleachers. All right, so it's a football field. All right. Where is that football field at? What? Near a school. What kind of school?
High school.
A high school. Why is it not a high school? Colleges have better football fields. They have more seating, right? So it's a football field, but it's not the Meadowlands, right? It's probably a high school. All right. How about a college? Could that be the RIT soccer field?
Well, no.
No surrounding infrastructure.
What is it about the structures that doesn't make it RIT?
I just look at it and say there doesn't seem to be enough infrastructure around it. You would expect more parking lots and more adjacency of buildings.
Exactly. So it's the adjacency to building, the presence of a large parking lot. If it was a college, it would probably be multiple buildings, not a single building. And a single building implies that it's probably a high school. Could it be a grammar school? Could it be a first grade through sixth grade? Yeah, well-funded grammar school that had a football field, right? But probably not. So now, think about everything you just did there, right? And this is actually the project I'm working on right now. I don't know how I'm going to solve this project. But the Department of Energy wants me to look at a scene and be able to do exactly what we just did. Say that's a football field, that's a high school building, these are parking lots. And then in addition to that, they want me to be able to separate those objects and be able to move them around. But that's a very, very difficult problem because there was a lot of thought that just went on. It happened very quickly inside your head, and you probably knew within a couple seconds looking at that what it was. But imagine trying to write an automatic algorithm to do that same sort of thing. All right, so photo interpretation is really one of the building blocks now that we need to build our remote sensing algorithms with, because the ability to look at imagery like this and do what we just did with those 7 cues, well, we should try to incorporate those as well as we can into any sort of algorithm that we develop to do processing. Right? If we can do that, it's only going to make the algorithms better. We can look at spectral signatures all day long, right? And whether or not it turns out that that's a spectral reflectance of a conifer tree, blue spruce, or an oak tree that has leaves, that's kind of hard to do just spectrally because they look spectrally very different, but their texture, if we went back to texture, would be very different. So bringing in that texture helps me distinguish between those two. But without that, it would be very difficult. All right. So we talked a little bit earlier about color infrared film and about camouflage detection and why it was invented. Well, here's the reason why. Back in the World War II sort of time frame, the people who made camouflage were pretty good, right? And if I look at the spectral signature, this is reflectance as a function of wavelength in the visible wavelength region from 0.4 to about 0.7 microns. So in this area right here, if you look at the solid curve, that was camouflage netting, okay? And the dotted curve was vegetation. right? And these two curves laid really nicely on top of each other. So to your eye, as long as they got the texture right, as long as they got the distribution of colors within the object right to make them look like trees, it would be very hard for you to tell the difference between a tree and a well deployed camouflage net. And that was the whole idea, right? But now, as soon as you were able to look a little bit further, color infrared film came along, we realized that the people who made camouflage didn't realize that chlorophyll was very highly reflective in the near infrared region of the spectrum. Right? So 0.7 to 0.8 microns. You got this really big rise in reflectance. Well, if the folks who made camouflage didn't do that, now it would stick out like a sore thumb if I could see in the near infrared. All right, so here's an image where we deployed 3 camouflage nets, right? And this is a color infrared image, and they stick out like a sore thumb, right? Because in these particular wavelengths, with color infrared film, the infrared reflectance of that camouflage was nowhere near what you saw in the trees, right? So they very clearly, able to be detected. Now, I wish I had the black and white image. I'm sorry, the true color image of this, so to be able to see them side by side, but I couldn't find it. Anyway, I was looking for it last evening. I know I have it somewhere. I just wasn't able to track it down. All right, so since then, camouflage makers have gotten really, really good. and these curves that we just showed previously are lying right on top of each other. And in fact, all the way out to about 2.5 microns, these things lie on top of each other. And even in the thermal infrared region, they got the elusivities right. And camouflage can now be electronically temperature controlled, so you can make it look different. So I mean, it's really, what the camouflage makers have done is really neat. If you go online and look for camouflage, you can see all the spectral signatures that they have out there right now. A couple companies have posted all their spectral signatures, so if you want to look at this stuff, it's all out there. All right. Now, here's another color infrared photo. This was in central Pennsylvania again. And, all right, so just looking at that image, what are we looking at? Roadways. And field. What does the texture in the field imply that it is? I think it's trees or shrubs or something alongside the roads.
Only trees, because if they did shrubs, I think they would be patterned better.
But if they were hand planted, for sure, right? All right, so they're trees, right? It's a fairly high altitude, so the tree crowns themselves look pretty small, but it's a very high altitude image. Right? What do you notice around the roadways?
Roadways are elevated a lot.
The roadways look like they're elevated a bit. How about the trees around the roadways? They're redder, right? So in color for red, what do we say that the redder tone implies?
Healthier.
More healthy vegetation, or more biomass, right? So what actually happened here was this is the middle of Pennsylvania, a lot of the highly traveled area by tourists and things like that, and they sprayed the trees along the sides of roads for gypsy moths, but didn't care away from the road because the visitors wouldn't see that. Right? So you got healthy vegetation with a lot of biomass along the roads because that's what sprayed, and gypsy moths were repelled from that area, but they just went in and ate up all the other areas. So if you walk 10 feet into the woods, you would notice there was no leaves on the trees any longer. But when you were traveling in the fall, looking at the pretty colors, all the leaves were still there. So that was sort of a neat image that we flew.
What do you mean by more biomass?
More leaves. Yeah, just more green stuff. All right. Now, when we start to talk about multispectral systems or cameras that look in many different wavelengths, there's a lot of different ways to do that. And the first way that folks did it was with multi-cameras. All right? You took multiple cameras. So this is a high-tech system from the, I want to say from the late 60s. And if you notice, there's 6 lenses here. There's actually 6 different cameras behind these lenses. And each camera had black and white film in it. And each lens had a different color filter on it. So now what we were able to do is collect 6 images simultaneously through different color filters. So you'd have different information captured on each piece of film. And then you would have to take that film and overlay it with one another so you can actually see maybe 3 bands at a time. You could print a color image or project a color image if it was positive film. And you'd be able to see a color rendition of the combination of any of those 6 bands. But it was one of the first times we were able to do that with a multispectral sort of approach. So here was the bands. They were 0.5 to 0.88, 0.8 to 0.9, 0.7 to 0.8. So really we kind of tried to center on areas that corresponded to the red, green, the blue, and the near infrared sorts of parts of the spectrum. But you can see that things look very different through those filters, just as you expect they would after having seen those spectral reflectance curves. Right? So here, what we start to do is just like you said earlier, we start to pick points on those spectral curves, but they're very discrete and simple. All right, now, let's see. What time is it? All right, we're going to stop there for today. And what I want to do next time, this wasn't in the set of notes originally, so I just put these in, and I didn't know copyright issues and all that, so I just copied them out of John's book and put them on here, because I didn't know if I could do anything else with them, but I will check. But what I want to do briefly is start to talk about the 2 different ways that we're going to look at remote sensing data. One is to use remote sensing data to make measurements, okay? To figure out how big things are, how tall things are, how high things are off the ground, right? And that's a field that we call photogrammetry. And I'm not going to spend a lot of time. I'm going to spend maybe an hour talking about photogrammetry with Max. And we're going to give you a lab to do photogrammetry so you get some experience doing it. And that's going to be it, all right? If you're interested in photogrammetry, in the spring there's going to be a course by Don Light in photogrammetry that is superb. Don is like a legend in the field of photogrammetry. Worked for the Defense Mapping Agency for forever, and at USGS and so on. And he's a consultant in photogrammetry for all those organizations still today. So if you're interested in that field, he has a great course. If you're interested further than that, then we have an Introduction to 3-Dimensional Geometry course, which is a computer vision approach to photogrammetry, taught by Harvey Rohde. That'll be offered. It's offered this quarter right now, but it'll be offered again next year. That would be a great follow-on to that. So if you're interested in that area, I'm going to refer you to that. The second part of remote sensing, though, is the use of this data for making radiometric measurements. Right? And that's what this course is going to primarily concentrate on, is the use of radiometric data for remote sensing to be able to figure out things about objects on the ground. Right? So you can really break remote sensing up into those 2 very broad fields. So I want to touch a little bit on this. I'm going to give you some exposure through a laboratory, and then we're going to put that away. So next time what I'm going to do is we'll go over the approaches. These are very, very fundamental photogrammetry concepts that we'll look at. And if you could do similar triangles, remember similar triangles? If you can do similar triangles, you got it down. All right, that's all it's going to take. And then I'm going to have Monica come in and introduce the first lab to you, so you can get working on that. So like I mentioned, we're going to try and have the first exam right before the break, and probably this first lab will be due right before the break also, so that you don't have to worry about the break. All right, but we'll get going on that next time. So, any questions?
Would you describe your exams kind of like the radiometry exams, where they're just like a lot of problems? There's a lot of things to do. You know what I mean?
I don't know yet. I haven't made any up yet. Okay. No, I mean, they're not going to be. I mean, radiometry, you could sit there and get it really deep. What's the radiance coming off of this surface at this angle above? You did that already in radiometry. We're gonna use radiometry now to attack these problems, but there's not gonna be long computational sorts of problems. There's gonna be the questions are gonna be more conceptual than they are quantitative for the most part. If I have to ask you a photogrammetry question, though, obviously that could be quantitative. So there'll be a mixture of them. All right.